Okay, thank you. Yeah, so as the title says, I will talk about a particular kind of symmetry of some functions that arise in trying to refine the enumeration of vertically symmetric ASMs. And as Ilse has preempted in the morning, the main part of this argument will involve a certain antisymmetrizer to determinant formula, which I think is of independent interest from the actual result that is proven here. And that might lead to more interesting applications in other currently open enumerative problems. Okay, so a quick outline. I will go over the refined enumeration of VSASMs and sort of tell the story of where these functions come from and why this particular kind of symmetry might be interesting. The main part of the talk will be to go from an antisymmetrizer formula to a determinantal formula, which will then make the actual argument quite easy. And in the end, I will go over some perspectives on this and talk about our original motivation for studying this problem. Okay, so I don't need to define what an ASM is, but just for clarity, I define what a vertically symmetric ASM is. So it's just an alternating sign matrix that is symmetric upon reflection by the vertical symmetry axis. Some thought will reveal that these can only exist in odd dimensions, and the central column of a vertically symmetric ASM is always fixed. So it has no zero entries, it's just 1 minus 1, 1 minus 1 alternating. So if you want to do some refined enumeration, like in the case of ordinary ASMs, the 1 in the first row is not particularly interesting. So there's two sort of obvious choices one could look at. The one we will focus on is where is the first 1 in the second row. This was done by Ilse and Manjil Sakia a few years ago. And there's a very nice product formula that tells you how many VSASMs are there that have the first 1 in the second row in a particular column. The story of this talk will be completing a previous attempt at proving this, which failed at the time, but which we made to work now. Before I go over that, I will make a quick detour to fulfill the unofficial subtitle of There Should Be a Bijection. So there's another obvious refined enumeration one could do, which is, okay, the first row has a 1 in a fixed position, but one could still look at where the unique 1 in the first column is. So the unique 1 in the first column in row I has this formula, which is transparently very similar to the formula we have seen before, which I hope I can go back to. There you go. So this product is the same, just the prefactor looks a bit different. Yeah, exactly. I mean, this sum is previously just one of these factors. Now we have an alternating sum. But still, it's not entirely dissimilar. And this was proven by Rasumov and Stroganov in the early 2000s. Because of this alternating sum, there's a simple relation between these numbers. Very simple relation between these numbers. Here's a pictorial illustration of this relation. So the number of VSASMs that have the unique 1 in first 1 in the second row in column I is the same as the number of VSASMs that have the unique 1 in the first column in row I or row I plus 1. There is no bijective proof of this. So I invite you, if you don't want to think about antisymmetrizers and determinants and formulas, I invite you to think about this problem as well. And there should be a bijection. I agree, but so far there is none. And some people think this is as hard as the ASM TSS CPP problem. But I think it's an interesting problem. Okay, now we head back to the actual story of how one can prove the refined enumeration in the second row. For this, I recall one way to prove the refined ASM theorem that was done by Ilse. So the refined ASM numbers, the number of m by n ASMs with the 1 in the first column in row I, given by a and I, and one can prove that these numbers satisfy a particular system of linear equations. and one can prove that these equations have a unique solution. Then it's just a matter of checking that the refined ASM numbers are a solution, and this is a proof of the refined ASM theorem. And one can find, so this linear system of equations can be found by using the operator formula for the first family of equations and just simple reflective symmetry for the second family of equations. The story of where these functions that we considered now come from is one can do a very similar thing for the problem of VSASMs and their refined enumerations. If one does this, one arrives at this linear system of equations, which is very similar. So just from computer experiments, computing these numbers and looking for a linear system of equations, one arrives here. Now this is a proved identity, yes. But which conjecture? This was not a conjecture anyway. This was proven 5 years ago already. Yes, and this is the proof that I present now. This is entirely possible. I don't know about that. I mean, we will get in the end to why we're even reproving this, because we have a different approach, and our original motivation for studying this was not so much reproving this refined enumeration. I will get to this in the end. Yeah. Yes. Yes. The range of J. The range of J in the summation is from. Yes, I mean it ends up being I. Yeah. But okay, I mean this is not a big problem. Okay. Yes. Okay. So one can find this linear system of equations conjecturally by computer experimentation. But if one wants to prove that the refined enumeration numbers that we're looking for fulfill this linear system of equations, one has to somehow combinatorially interpret the numbers that appear. And in this refined enumeration, we only consider I going from 1 to n. These other numbers that appear also need some combinatorial interpretation. This is what Ilse and Lucas Riegler did. In 2014, they found interpretations for these numbers in terms of partial monotone triangles. So monotone triangles where you cut out certain regions. And to prove that the refined enumeration of VSASMs works using this argument, one then has to prove that these two objects are equinumers. One has to show that these two interpretations agree and give the same numbers, then one is done. Okay. In trying to do this using sort of operator formula approach, they arrived at the following family of multivariate functions, which is what the rest of this talk will be dealing with. So here is a function. It's an antisymmetrizer, which we have seen a few times already today, of some function depending on n variables. If you remember Ilse's talk, products of this form have appeared quite extensively inside of antisymmetrizers, but this prefactor is something we have not seen in this form in previous talks. It's a rational function, a priori. Yes. Okay, it's just a definition. What they proved is that if one can show this symmetry of this rational function, so you exchange all the variables with their inverses, and then everything that happens is you just get one simple factor coming out and everything else stays the same. If you prove this symmetry, then the refined enumeration follows. So the question of this equinumerosity of these two interpretations boils down to proving this. Okay. Problem is that they were not able to prove this. This is maybe not so surprising because inverting the variables in the antisymmetrizer is not so simple. It's hard to keep track of all the permutations and what the antisymmetrizer actually does to them. But they conjectured that it's true anyway. Okay. And now we have managed to prove this, which is what the symmetry that the title is about is. So we have actually managed to prove something slightly better. We don't invert all variables, but if you just invert any of the variables, the function stays the same except for a simple factor that comes out. In particular, this gives a new proof of this refined enumeration that uses only operator formula approach, similar to the refined ASM theorem. Okay. So how did we prove it? So what changed in the intervening years and why were we able to prove it now when they were not able to prove this 10 years ago? As I said, the substitution in the antisymmetrizer is difficult. It's hard to keep track of all the things that happen. So the maybe naive idea is to just transform this antisymmetrizer into a determinant somehow. In the determinant, if it's of a sufficiently nice form, I mean a form like this, substituting xi by xi inverse might be very simple. So the form that we're looking for is a determinant where the ith row depends only on the ith variable, and the functions in the columns look the same. So the first column looks the same across the whole from row to row. And here, substituting xi by xi inverse might be a very simple problem because then it might just be a matter of pulling out a factor from the determinant and then you're done. So this is the hope. And this hope is, of course, substantiated somewhat by the antisymmetrizer to determinant formula that we have seen in Ilse's talk in the morning. So I write it in a slightly different form than she did, but it's the same statement. We follow as a product of this form, I less than equal to j, some expression in j minus some expression in I, which these algebraically independent variables are just placeholders for some, let's say, rational expressions in the variables. One antisymmetrizes this product, and the result is a very simple determinant. So this is to me at least, very surprising statement. It has a very simple linear algebraic proof, just through using the recursive structure of the antisymmetrizer and what's it called? Cramer's rule. So just Laplace expansion, essentially. And as Ilse said, it also has a combinatorial proof. Yeah. Okay, so what this asym had space on this page anymore, it means you permute the y's and the z's amongst themselves and by the same permutation. So you apply the same permutation to the y as you do to the z, and you don't mix y and z. And the purpose for writing it like this is simply that you can plug in any algebraic expression in variables xi and you will get a result. Okay. So in our function that we're considering, if one takes s to be 0, this prefactor that appeared in the antisymmetrizer disappears and you just have a product that is of this form. So a product I less than or equal to j, some expression in j minus some expression in I. So we can apply this lemma and immediately get it into a determinantal form. And from this form, it's very easy to see the symmetry that we want. If you replace xi by xi inverse, you just exchange the role of the two parts of the difference. And so everything that happens is a sign, which is what we wanted to show in the case s equals 0. Okay, very simple. If s is not 0, then you get this factor in the antisymmetrizer, and you cannot simply apply the antisymmetrizer to determinant lemma. You have to think of something different. And the thing that you can think of is you take a computer and you look at some of these things and you try to find a determinant that has a similar form. And you hope that the computer gives you such a form. And indeed, this works. So what we first did, or what Ilse actually first did, you take, so this S, it was maybe very short, the parameter S is allowed to be between 0 and floor of n plus 1/2. So the case S equals 0 we can do. The next case we looked at is the other end of this region. So S is n/2. And then one can also find a determinantal formula like this. It looks very similar to the one we previously had. So this is just the value of S. Writing S equals n/2 might be a problem if, depending on the parity of n. What n? N is the number of variables. Yeah, just in the interest of keeping this in one line, it was a bit nicer to not include the variables in R here. Okay, and again, from this expression, the symmetry that we wanted to prove follows immediately. If you exchange xi by xi inverse, these two things more place. And then you have to think about what happens to this factor in the front, but this is also easy because xi, x to the -2 minus x to the -1, just x squared minus x times some factor.
Nice question. Here you're applying everything to the function x squared minus x. Does it apply for
this is something that we get to in the end. That's something we are working on at the moment. That's obviously the interesting question. Yeah. Okay, and so from these two things you get a sign. From the factor in front, you get a factor that you can just pull out of this row, and you again deduce the symmetry that you want to deduce about this function. Okay, so we did the case S is equal to 0. We did the case S is equal to n/2. Now what about the other cases? The very satisfying answer is that somehow it also has a determinantal expression of a very similar shape that you can find by asking the computer to search over parameters and waiting for the computer to give you an answer and then guessing the pattern. And this, I struggled how to write this in a form where you see it easily, but basically this determinant is a mixture of the two extremal cases. So in the first 2s minus 1 columns, here you just have negative exponents from -2s minus 1 to -1, which is the same thing that we had in the case where s is just n/2. And in the remaining columns, it just looks like the case s is equal to 0. So somehow nothing particularly bad happens outside of these extremal cases, and it's just a combination of these two cases. And importantly, of course, again, from the shape of the determinant, you immediately read off the symmetry result. Because again, you just get a sign from flipping these two things in the difference and a very simple factor from the factor in front. So you get what we wanted to show. Okay, and so as I mentioned at the start, this, from one perspective, this completes an operator formula proof of the refined enumeration of VSASMs. It proves something at least algebraically slightly stronger because we proved symmetry in just one variable and not just in all variables. Whether this has implications for enumeration is something we're currently looking at. So we have not had much time to look at it yet, but this is work in progress. Okay. So finally, why did we consider this problem? It's not maybe super interesting to reprove a refined enumeration result that was already known. We originally wanted to solve a different problem that involved expressions of this form. So you have some anti-symmetrizer, some product over a subset of the variables, and then this product I is less than or equal to j, some expression in j, some expression in I. We wanted to write this as a determinant or at least get some nicer formulas, and we were not able to do this. So we turned to, or Ilse showed me this problem that she worked on previously, and we have managed to solve this now. To be specific, and in the interest of Philipp's talk tomorrow, this is the problem that we actually tried to work on. So we tried to enumerate the number of m by n ASMs that have a s by s square of 0 entries in some corner. Okay. If one does this using the standard operator theory, operator formula, you can arrive at this anti-symmetrizer where the UVW serve the same function as they did in Ilse's talk in the morning, which has this shape, right? It's a product over some subset of the variables times an expression in I less than or equal to j. Huh? Yeah, this is again a matter of notational convenience. You just specialize the yi to pick one. So I guess vxi plus w in this case. Okay, and writing this as a particular kind of determinant seems to be an interesting problem to statistical physics community, which we will hear more about tomorrow. Maybe the fact that we have managed to write this algebraically similar expression as a determinant might be a hint on how one could attack this problem as well and write this in a determinantal form. Yeah, this is basically all I wanted to say, I think. Okay, thank you.